So let's look at this carbon. We know this carbon has a lone pair of electrons and it has 3 bonds. So therefore, we know this carbon has a formal charge of -1. And we know how to determine the formal charge of an atom. We find out how many valence electrons that atom is supposed to have and subtract it by the number of valence electrons that atom actually has. And it's a simple formula to determine the formal charge of an atom. So we know this carbon has a formal charge of -1, which means it has the charge of 1 electron, 1 negative electron. That's how much negative charge it has. However, what if we have this carbon? Well, again, we can determine the formal charge of this carbon, and we know this carbon would have a formal charge of +1. And again, we find out how many valence electrons carbon is supposed to have and subtract it by the number of valence electrons it currently has. So if we did that, we would get +1. So we know this carbon has a formal charge of +1. So now that we know this carbon has a formal charge of -1 and this carbon has a formal charge of +1, this is not stable. A key rule of thumb when dealing with chemistry is that nature hates charges. Nature hates that this carbon has this localized negative charge and that this carbon has this localized positive charge. That's unstable. This localized negative charge with that high charge density is unstable. Nature hates charges and tries to destroy charges. So, now that we know that, let's do a thought experiment. Let's imagine we have these 2 negatively charged electrons with their negative charge density. We know these negatively charged electrons don't want to be near each other. We know they will repel and they don't want to be near each other. For example, what if we push this negatively charged electron towards this one? Well, if we did that, if we push them together, we would have this region with high negative charge density. We would have this localized negative charge, this negative charge localized in this region with this high charge density, which we know is unstable. We know this is unstable. These negatively charged electrons want to repel each other because when we force them together, again, we have this localized charge, which is high in energy. This is unstable and high in energy. And we know with Coulomb's law, essentially the closer charges are together, the higher the energy in the system. But again, the point is that nature hates this localized negative charge with this high charge density. So nature likes to delocalize charge. It likes to spread out that charge and to delocalize that charge. And spread out that charge and delocalize and repel that charge because that's more stable, that delocalized negative charge. So now let's do another example. Let's say in this example we have this negative charge and this positive charge. What would happen if we push this positive charge nearby? Well, if we push this positive charge nearby, they're going to destroy each other. Because in this region, we have negative charge, but we also have positive charge, so they'll cancel out each other. So now we have no charge. We have no charge density, which is stable. Remember, nature hates localized charge. Nature hates charge density. But now we're destroying charge, so now there's no charge here. So that's stable. Nature likes destroying charges. So when we push that positive charge nearby, we're destroying charge. So again, we know nature hates charges. So now that we know this, what's going to happen if we have this carbon with this formal charge of -1, this negative charge, and this carbon with this formal charge of +1 with this positive charge? We know they're going to react, and that's why molecules react. They react because when they react, they essentially destroy charges, and these electrons go to a lower energy state, a more stable state. But so now we know these reactions are these atoms are going to react to destroy the charge. So again, essentially these lone pairs of electrons will attack the carbon, forming a bond. And when they form a bond, they'll destroy the charges. Because if you were to find the formal charges of these 2 carbons, they would have formal charges of 0. Because we've destroyed the charge, so this is more stable. This is a lower energy situation, so this is more stable. So that's why molecules react. They react to destroy charge, because we know this localized negative charge and this localized positive charge is unstable. So when they react, they destroy charges. So let's do, and again, something important to realize. So we know molecules react because one molecule has negative charge and the other molecule has positive charge. So when they react, they destroy the charges. So the molecule that has the negative charge is referred to as a nucleophile, while the atom that has the positive charge is referred to as an electrophile. So this is just a little bit of terminology. So let's do another example. Let's say we have these 2 molecules. So again, we know this carbon if we were to find its formal charge, we know this carbon has a formal charge of -1. We find out how many valence electrons it's supposed to have and subtract it by the valence electrons it actually has. So we know this carbon would have a formal charge of -1. But what about this carbon and this chlorine? Well, if you were to find the formal charges of these atoms, they would be neutral. They would have formal charges of 0. However, something else to keep in mind is that this carbon has an electronegativity of 2.55, while this chlorine has an electronegativity of 3.16. So we know this chlorine is more electronegative, and in fact, chlorine is very electronegative, one of the more electronegative atoms in the periodic table. So what does that mean if this chlorine is more electronegative? That means it hogs negative charge. This chlorine likes negative charge, so it's going to steal negative charge density. So this carbon with its electrons, we know this chlorine is more electronegative, so it's going to steal that negative charge density. It's going to hog that negative charge density. It's going to steal that negative charge electron density and steal it and push it towards this chlorine. So what happens when this chlorine hogs and steals some of that negative charge density? Well, now this chlorine will have a partial negative charge. We know it's hogging and stealing that negative charge density, so it's going to have a partial negative charge. And we know if it's stealing negative charge, this carbon is going to lose negative charge density, so it's going to have a partial positive charge. And that's what this symbol means. This symbol is essentially the symbol for partial charge. So this carbon has a partial positive charge, and this chlorine has a partial negative charge due to the difference in electronegativity. So now that we know this carbon has negative charge, this carbon has some positive charge, so we know they're going to react. These charges want to destroy each other because nature hates charges. So when they react, they're going to destroy some of that charge. So this is essentially going to attack this carbon. Then this bond breaks, and these electrons will fall in this chlorine. So when we do that, we'd be left with these molecules. So again, these are our initial molecules, but it reacts, pushing these electrons here, forming these final molecules. And this makes sense, because now in this final situation, we have none of those partial charges. So we've destroyed those partial charges, and now we're just left with one formal charge on this chlorine. So again, initially we had a formal charge and two partial charges. Now we only have one formal charge. We don't have any partial charges because carbon and carbon have the same electronegativity, and carbon and hydrogen have about the same electronegativity. So we went from one formal charge and two partial charges to one formal charge. And not just that, Remember, chlorine is more electronegative than carbon. So if we had to have a formal charge of -1, if we, no matter what, had to deal with a formal charge of -1, it's better for the chlorine to have that negative charge than the carbon, because then chlorine is more electronegative, so it likes that negative charge. So if we have to deal with a formal charge of -1, it's better for chlorine to have that negative charge. So we know this is more stable. This situation makes more sense. And not only is chlorine more electronegative, so it likes that negative charge, but not just that, we know chlorine is larger. Because again, we know in this situation, this carbon has that formal charge of -1, and in this situation, the chlorine has that formal charge of -1. However, this chlorine is a larger atom. It has a larger radius. So that formal charge of -1 is spread out throughout a larger atom. That negative charge is delocalized throughout a larger region, so that's a smaller charge density. However, this carbon is small, so that formal charge of -1 is localized around the small carbon atom, so that charge is going to be localized with the high charge density, which we know is unstable. But the point is, these molecules react because this atom had some negative charge density and this atom had some positive charge density. So they wanted to react to destroy those charges. And again, the molecule that has negative charge is referred to as a nucleophile. So this molecule acts as a nucleophile, while this molecule acted as an electrophile, where this carbon was electrophilic, because again, it had positive charge. So what are some examples of nucleophiles and electrophiles? So here are some common nucleophiles you'll see in biochemistry, and here are some common electrophiles. So what are some common themes we see? Well, we see a lot of these nucleophiles have these lone pairs of electrons. Because again, when we have a lone pair of electrons, we have an orbital with these two electrons. So we have some localized negative charge. We have a partial negative charge here. So again, whenever we have a lone pair of electrons, we have some partial negative charge. And not just that, Again, we know the sulfur is more electronegative than carbon, so it's also pulling some negative charge density. So again, that's why we have this partial charge. We know this carbon, if we were to find the formal charge, we would have a formal charge of -1. So again, here we would have a partial charge. Here we would have partial charge, negative charges. Here we have a formal charge of -1, which is actually stronger negative charge density. So therefore, this is a stronger nucleophile. The more negative charge you have, the stronger the nucleophile. So formal charges of -1 is more negative charge than a partial charge. But again, we have these lone pairs of electrons, so we have these partial charges. So again, but whenever we have some localized negative charge, we have nucleophiles. So what are some common themes of these electrophiles? Well, common theme is, you'll see, for example, let's look at this molecule. We have this carbon with an electronegativity of 2.55, and we have this oxygen with an electronegativity of 3.44. So we know this oxygen is more electronegative than this carbon. So if this oxygen is more electronegative, we know it's greedy. It's going to hog that negative charge density. It's going to steal some of that negative charge density. So when it steals some of that negative charge density, now it steals some negative charge, so this carbon loses some negative charge. So when this carbon loses some negative charge, it gets a partial positive charge. So that's a common theme with electrophiles. You'll see one atom next to another atom that's more electronegative. So the atom that's more electronegative is stealing negative charge, creating a partial positive charge. So that's where we see our electrophiles. That's a common theme you'll see with electrophiles. So again, here's another electrophile, because again, we have a carbon next to nitrogen. Nitrogen is more electronegative, so it steals negative charge. It hogs some negative charge density, so we have a partial positive charge. Here, we have this phosphate next to these oxygens. We know oxygen is very electronegative. So we have all these oxygens stealing negative charge density. So this phosphate is going to lose a lot of negative charge density. All these oxygens are stealing negative charge density. So this phosphate is very electron deficient. So we have this strong partial positive charge. So this phosphate is electrophilic. So again, that's a common theme with electrophiles. But again, we know there's a difference between a partial charge and a formal charge. We know, for example, this carbon and this fluorine, we know this fluorine is more electronegative. So this fluorine is stealing negative charge density. So we have this partial positive charge. But here we have a formal charge of +1. Because again, we would find the number of valence electrons carbon's supposed to have. Then we would find the number of valence electrons carbon actually has to find the formal charge. So again, formal charges are stronger than partial charges. So this would be the strongest electrophile. This guy with this formal charges is the strongest electrophile. And then these would be weaker electrophiles. But again, so that's the common theme with electrophiles, either partial, formal, positive charges or these partial charges. But now, so we know we have these nucleophiles and these electrophiles, and we can have these nucleophiles react with these electrophiles, and we can mix and match these reactions. For example, maybe this nucleophile reacts with this electrophile, or maybe this nucleophile reacts with this electrophile, or maybe this nucleophile reacts with this electrophile, etc. Whenever we have localized negative charge and localized positive charge, we can have a reaction. So let's do an example. Let's say we have this nucleophile and this electrophile. We know they can react. We have this localized negative charge with this lone pair of electrons, and we have this localized positive charge, because again, this oxygen is hogging negative charge density. So again, we have that partial positive and partial negative. So again, nature hates charges. It wants to destroy these charges. So now these molecules will react. So these electrons will attack, forming a bond. And when we form that bond, we push these pi electrons up on this oxygen. So when we do that, we form this high energy intermediate, and then the electrons will move, forming this product. So now we've reacted the molecules together. And again, the idea was this molecule had some negative charge, this molecule had some positive charge, so they attracted and they reacted to form this molecule. So again, the molecule with the negative charge is the nucleophile, while the molecule with the positive charge is the electrophile. So we have this nucleophile react with this electrophile. But something really important to realize is, let's say we had this nucleophile and an electrophile, and let's say we were in an acidic solution. So let's say we were in an acidic solution with a lot of hydrogen ions, and really we would have a lot of hydronium. But what happens when we're in an acidic solution? We're going to protonate these molecules. So we're going to protonate this oxygen. So what happens when we protonate this oxygen? Well, now it gets protonated, and when it gets protonated, now it has a formal charge of +1. So now we have strong positive charge density. So what's going to happen when we have strong positive charge density on this oxygen? It's going to pull negative charges even stronger. When we have this formal charge of positive 1, it's going to really strongly pull on negative charges. So it's going to steal very strongly, it's going to steal negative charge density. All these electrons here, this positive charge is going to pull on those negative charged electrons. So we're going to strongly pull electron density, negative charge density. So we're going to create a stronger electrophile. We're going to create a stronger electrophile, and we're going to create a more reactive electrophile. So again, originally we had an electrophile. However, we protonate this guy. Now it pulls more negative charge, creating a stronger electrophile. So now we have a more reactive electrophile. So the rule of thumb is that acidic conditions create stronger electrophiles. So that's a general rule of thumb. For example, let's say we had this electrophile. What would happen if we put it in an acidic solution and it got protonated? Well, if it gets protonated, now we have this formal charge of positive 1, which pulls more negative charge density, creating a stronger electrophile. So again, the point is acidic solutions create stronger electrophiles, stronger partial positive charges, and more reactive electrophiles. And sometimes you hear about reaction being acid catalyzed. A lot of the time that's why. Because certain reactions can be acid catalyzed because when we protonate it in acidic solutions, we create more stronger electrophiles. So again, acidic solutions create stronger electrophiles. However, let's say we have the same reaction, and let's say we have this reaction in a basic solution with high hydroxide. So in a basic solution, what's going to happen? Well, that hydroxide, that basic solution, is going to deprotonate the nucleophile. And when it deprotonates the nucleophile, we create this formal charge of negative 1, so we create a stronger nucleophile. So again, originally, we had this partial negative charge, but we're in a basic solution, so we steal hydrogens, create a formal negative charge, so now we have a stronger nucleophile. So the rule of thumb is that basic conditions create stronger nucleophiles. Basic conditions create stronger nucleophiles. For example, let's say we had this nucleophile. We have this nucleophile with this partial negative charge. However, if we put it in a basic solution, it's going to deprotonate that hydrogen, forming this formal negative charge of negative 1, creating a stronger nucleophile because now we have a formal charge of negative 1. So now we have a stronger nucleophile, a more reactive nucleophile. So basic conditions make stronger nucleophiles. So normally we have a hierarchy. For example, we know this carbon is electrophilic because look, it has 1, 2, 3 bonds to oxygen. And we know oxygen is very electronegative, hogging electron density, stealing negative charge density. So therefore, we're going to have a relatively electrophilic carbon. How about this carbon? Well, it has 2 bonds to oxygen. So again, oxygen's electronegative, it's hogging negative charge density, so we're going to have an electrophile. How about this carbon? It has 1 bond to oxygen, which is going to pull negative charge density. So we're going to have this hierarchy. This carbon's going to be most electrophilic with the highest partial positive charge, so it's going to be most electrophilic because it has 3 bonds to oxygen. And then this guy will be less electrophilic because it only has 2 bonds, and this guy will be even less electrophilic because it has 1 bond. And this carbon is not going to be electrophilic because again, hydrogen and carbons have the same electronegativity, so there's no partial positive charge here. So this atom is not very electrophilic. Then again, but remember, formal charges are the most reactive. So this carbon with the formal charge of positive 1 would be the most electrophilic. So we would have this hierarchy. This is the most electrophilic, this is the least electrophilic. And what if we had this atom? Well, again, this carbon has 2 bonds to oxygen and 1 bond to nitrogen. And we know nitrogen is more electrophilic, more electronegative than carbon, so it's still pulling some negative charge density. So this carbon electrophilic reactivity would be around here, because here we have 3 bonds to oxygen, here we have 2 bonds to oxygen and 1 bond to nitrogen, and here we have 2 bonds to oxygen. So this would be the most electrophilic, then this guy, then this guy, then this guy, etc. And what about nucleophiles? Well, again, this oxygen has a formal charge of negative 1, while this oxygen has a partial negative charge. So this is more stronger negative charge density, so this is a stronger electrophile. Then this guy's a little weaker. And what about comparing this oxygen to this fluorine? Well, this fluorine is very electronegative. So something important to realize is because this fluorine is electronegative, it wants to hog all its negative charge. It wants to keep these lone pairs of electrons and hog all that negative charge. So therefore, we know for this to act as a nucleophile, these electrons have to attack and it has to donate these electrons. But this fluorine being so electronegative, it wants to hog the negative charges. It wants to hog these lone pairs of electrons, so it doesn't want to donate them, so it's not very nucleophilic. And then this carbon has no lone pairs of electrons, so it's not nucleophilic at all. It's a very weak nucleophile. And this iodine, we see it has this formal charge of -1, so it has a lot of localized negative charge, so it's a strong nucleophile. And not just that, this is a large atom. It's a large atom with these large orbitals, so it's more polarizable, so these negative charge density can more easily attack, which makes it more nucleophilic. But again, so we have this hierarchy. But the key point is, formal charges are more nucleophilic than partial charges. And when comparing the atoms, the more electronegative, the weaker the nucleophile. So again, we have this hierarchy, but notice something. These carbon molecules are not very reactive. This is a very weak electrophile, and this is a very weak nucleophile. So we know these carbon skeletons are not very reactive. And in fact, that's precisely why a lot of life is built upon these carbon molecules. For example, we have these fatty acids, which have these carbon skeletons, and these carbohydrates, which have these carbon-carbon bonds, and these proteins and polypeptides, which have a lot of carbon-carbon interactions. Because these carbons are very stable. They're very stable. They're not very reactive. This isn't very electrophilic, and this isn't very nucleophilic. So they're very stable, and they're not very reactive. So they make good components of life for organic molecules and for life because they're not very reactive. So now let's say we had this nucleophile with this formal charge of -1, so we have this nucleophile. We know it's going to want to react with these molecules. So which molecules are going to react with? When this nucleophile is looking at these molecules, what is it going to see? Well, it's going to see the charges. For example, we have this formal charge of -1, we have a formal charge of -1. So again, but here we have a partial positive charge. So that's a good candidate because we have this negative charge nucleophile. So we have this partial positive charge, so that's a good candidate for a reaction. And here we also have a partial positive charge. But notice here we have a carbon bonded to 3 oxygens. Here we have a carbon bonded to 2 oxygens. So this carbon is going to be more electrophilic. It's more oxygens are stealing negative charge, so we're going to have a stronger partial positive charge on this carbon. So this is a strong electrophile. So this is a good candidate for a reaction. We also have some other relatively electrophilic carbons. And then here we have very tiny electrophilic carbons because again, they're bonded to oxygen pulling negative charge density. But again, this nitrogen wants to react and it's going to look what is the best molecule to react with. And we see this is the most positive molecule and this is the most negative molecule. So therefore these molecules are going to react. All this nitrogen sees are these positive charges because it's looking for a positive charge to react with. So this is the reaction we're going to have. However, something important to realize is this localized negative charge creates a nucleophile and this localized positive charge creates an electrophile. However, this nucleophilicity is a kinetic property. If this molecule is a strong nucleophile, that's a kinetic property. And that just means it's a strong nucleophile. It has a lot of negative charge, so it's going to react quickly. It's a kinetic property. Nucleophilicity and electrophilicity are kinetic properties. It says the rate that this reaction is going to react, how quickly these reactions are going to react. If this is a strong nucleophile, it's going to react quickly. If this is a strong electrophile, it's going to react quickly. It's going to have high kinetics. However, when this reacts, it's going to form a bond and then this bond's going to break and these electrons are going to fall on this guy. We're going to form these products. However, these products are incredibly unstable. We have this formal negative charge of 2, -2 charge, which is incredibly unstable. So then it's going to react, reforming these original molecules. So therefore, just because this is a strong nucleophile and this is a strong electrophile, that means, yeah, they're going to react quickly, but it doesn't mean this reaction is going to be very stable. And once this reaction reaches equilibrium, once this reaction reaches equilibrium, the vast majority of the molecules are going to be in the form of these original molecules. So just because this is a strong nucleophile and strong electrophile doesn't mean when it reacts, it's going to favor these products. And in order to determine once this reaction reaches equilibrium, if it's going to favor these guys or these guys. In order to determine that, we need to quantify the stability of this guy and compare it to the stability of this guy. So how do we do that? Well, what we need to do is we need to imagine this guy as an acid and find the pKa. If we find the pKa of this guy acting as an acid, the pKa of this guy will tell us about the stability of this conjugate base. And then finding the pKa of this guy will tell us the stability of this conjugate base. So finding out the pKa's of these acids, we can quantitatively determine the stability of these guys. So therefore, we can determine the stability of these guys and determine once this reaction reaches equilibrium, will it favor these molecules or these molecules. So if you're interested in these pKa's and how to determine once this reaction reaches equilibrium, whether it'll favor these guys or these guys, I have a link of that video below.